So good morning everybody, myself Acharya Vishvendra. Today I'll discuss a video on the modes of heat transfer. So heat transfer basically involves three different processes: conduction, convection and radiation. Conduction involves transfer of heat or energy without transfer of bulk matter. Convection involves transfer of heat or energy with the transfer of matter. And radiation involves electromagnetic radiations, and it is the fastest mode of heat transfer. Then we have Fourier's law. Suppose this is a cylindrical structure having an area of cross section A, length L. So the rate at which heat flow between the two ends is given by minus K, T2 minus T1 by L. After solving, it comes out to be delta T by R thermal, where R thermal is L by K, which is called the thermal resistance. So this is the Fourier's law of heat transfer, that rate of heat of flow between 2 points is proportional to the temperature difference. Now there are various applications of the concept of thermal resistance. So R thermal is L by K. So if we have a cylindrical cross section, we can say that area is pi R square. So for a cylinder, thermal resistance is L upon K pi R square. Whereas if we have frustum of radius R1 R2, so pi R square can be written as pi R1 R2. So that will be R thermal. Next, if we have this type of cross section in which heat can flow only in the region from R1 to R2. So we take effective area as pi R2 square minus R1 square. Whereas if heat flows, sidewise, I mean radially, so we have to integrate the expression, and the final expression is 1 by 2 pi Lk log R2 by R1 by C. In case of cylindrical surfaces, we need to integrate that expression, and R thermal is R2 minus R1 by 4 pi K R1 into R2. We have another case, we have two cylinders R1 R2 having different conductivities, so just take them in parallel, and our thermal is R1 R2 by R1 plus R2. Next we have a question that there is a rod, ends are at temperature T1 T2, we need to find temperature at a point X. So in a steady state both rates of heat are same, so the heat flowing through this is equal to this, so this is H1, this is H2, so equating the two terms, and after final calculations we get temperature as T1 minus X by L, T1 minus T2. Now if we draw the graphs, then graphs will be a straight line with negative slope, positive intercept, tan theta will be T1 minus T2 by L. We have another important question, that if we have a composite rod, on one side we have K1 A1 L1, on other side K2 L2 L2. This rod is maintained at T1, this rod is maintained at T2. Then the interface temperature can be found by this analogy. It has been derived using this law. You just make the heats equal from the two sides. So heat from this to this is H1, this to this is H2. So H1 is equal to H2, from where you get the result that T naught is K1 A1 by L1 T1, K2 A2 by L2 T2 upon K1 A1 plus K2 A2 by L2. So this shortcut you can remember, you can recognize it, and you can use it to solve your questions quickly and to bypass any sort of calculation involved as per your wish. Now there is an important case: if rods are identical in shape and size, that means A1 is equal to A2, L1 is equal to L2. T naught here comes out to be K1 T1 plus K2 T2 by K1 plus K2. So you have seen that we have covered a topic of about 1 hour duration in a video of 3 to 4 minutes. It's just to optimize your time and energy and to give you what is required to crack the exam. So just study with a pattern, just study with an optimization video. I hope it works for you. If you have any doubt, you can ask in the doubt section. Thank you and have a nice day.